Hello, my dear students, once again, class number 7, and we are going to talk about aircraft structure, airplane actually structure, and it comes about inner structure. But before we get started, once again, let's come back to matters that we been discussed previous time. Look at this. What we've been talking about mostly about categorizing of airplanes by their general appearance, let's say, but their outer features and their shapes and combination of the shapes and combination of different aircraft aggregates resulted in hundreds and hundreds of variants of design of aircraft, depending on what. Next, it comes about another type of classification. You already understand very well that aircraft, airplanes may be classified, categorized, depending on the purpose. Like, for instance, civil, military, and inside of this military and civil, also another classification, like passenger, cargo, medical, firefighting, agricultural, rescue airplanes, and so on and so forth. By their, in military group, also by purpose, depending on what they going to do. It's maybe reconnaissance, it's maybe fighter, attack plane, it's maybe a bomber. Bombers may be different. There are so-called front bombers and strategic bombers, and we may continue. Depending on the flight speed, they are usually divided onto, do forgive me, I will reject the call. Now do forgive me. Depending on what I was saying. I hate phones time to time, really. Depending on the flight speed, airplanes may be categorized onto at least subsonic and supersonic, at least. And all those classifications, they are represented in different way in different literature. Right now, we will come back to the slides that we have already seen, and it shows us airplane aggregates, actually, not airplane parts. And once again, it comes about the general arrangement of airplane. Next, we see in more details. You already understand, I hope, very well, the purpose of each element in the airplane structure, in the airplane outer general structure. And I propose you to take looks inside. What is inside of airplane? Well, there is a picture, a very popular modern passenger jet. Take a look. Right now, we are already watching something inside and outside and inside, but it's still not deep inside. And now let's take a look deeper. Looks very different, yes? And one more airplane, and seems like its inner appearance, it's regular, it's has some repetitive elements, but its inner appearance, inner structure is quite different from what we get used to see. Next, what it's remind you, what it looks like. I place it here for purpose, two photos. Simultaneously we see two quite different structures, but as for me, they're very similar. What we see at the bottom. It's unfinished, no, half-assembled aircraft without inner components, without its passenger deck in big passenger airplane. But it's without all inner elements, including inner skins, interior skins. Certainly looks very similar to this top photo. And this top photo, it's photo in a Britannic Museum of Nature. It's a skeleton of big whale. What is inside of a craft actually is sort of the skeleton. And I should say that a craft as a whole is rather similar in their composition to the body of any human, to the body of big animals. What is so similar at all? No, above the all, we have skeleton and skin. A craft either has skeleton and skin. And our task now is to understand and to give names, to understand names of elements of the skeleton and understand the principles the skeleton is composed on. No, in front of you right now, once again, fuselage half empty, as you might see, even deck, even passenger floor is yet absent. It's one of the passenger aircraft produced in our former Soviet Union countries, and you see what it looks like. It has some cylindrical skin, outer shapes, and longitudinal elements and so-called transversal elements, which are responsible for the shape of this fuselage. Now it's quite clear it has some additional elements. What right now we need, for instance, to place here the floor. And these supportive elements also in transversal direction, so-called beams, placed here. Whether it's the only way we may create the structure or not, like skin supported with thin elements. Hundreds of times maybe already mentioned that variety of aircraft, of airplanes, not even all aircraft, variety of airplanes, appearance, variance, design, it's really infinite. And the same is reflected next in the inner structures of aircraft, of airplane and helicopters. No, practical is the same. Maybe that whale was skeleton of this whale on the photo of Britannic Museum. I hope you see very well inner structures of the fuselage, practically start assembling and half assembled already. And what I have found. I've said you that this pilot handbook, the chapter name, it's looks suspicious for me. Aircraft construction, it's not the same like aircraft structure, and it comes about aircraft structure. And I was sure that I've seen another book where we have more detailed information, let's say. And preparing to your classes, I'm trying to find some another books for you, something for illustrations, for bright illustrations for you instead of drawing in front of you. And what I have found, look, Federal Aviation Administration USA, they have special site, and in their site a lot of books. Seems like the whole this pilot handbook, so-called the whole pilot handbook is produced by this FAA organization, was maybe copied, maybe revised by some another authors, and some things similar, but they are given shorter and so on. So pilot handbook you already have. These chapters I'm going to download to you. Some things I took only as chapters, some things as whole books. I will download for you. Once again, not for your complete reading, studying by heart, but in order you have some means for your studying, and maybe some of these books will be useful for you right now or in the future. No, I'd like you to have these books, let's say. Well, let's continue. And additionally, we will use additional slides, let's say. Now, in this aircraft structure chapter, I have found very interesting thing to show to you. Oi, no? Here is one more aircraft chapter structure. Aircraft structure chapter. No, really, I was surprised that I have found some similar things, but with different content, completely different content. You see, here is chapter 2, here is chapter 3, and chapter 1. But beginning and explanation, it's rather similar. Так, somewhere here it was good picture to explain to start explanation, let's say. Now here is the structure of airplane divided onto some aggregates, not everything we may agree with, in particular this power plant, what power plant, here it's not power plant, it's something like cooling of power plant. The same as landing gear cooling, no, the fairing maybe, cooling, fairing, doesn't matter. What is interesting for us right now? While flight airplane is loaded with external loads. And these external loads might be of some kinds of nature. Now, above the all, of course, it's the weight of aircraft structure itself. The aircraft structure that we have seen in slides, this structure itself, it has weight. Plus to this, to the weight of this structure, it will be added the weight of the crew and payload. Payload, I mean, either passenger or cargo, whatsoever, or maybe weapon. Next, compulsory we need to have fuel in the airplane. Next, fuel is for engines. Engines also may be placed in different place of aircraft, and depending on this, they whether do aircraft life more simple or create more difficulties to aircraft structural life, to aircraft stresses. And all those forces, they are somewhere here. They are all those forces may be calculated and represented in the view. Crazy woman, where did it disappear? No, don't pay attention yet. They may be represented in the view of special charts, which show the loads in each cross-section of the aircraft. No, something like this. Now you see the chart of loading the wing in particular. And to the weight, additionally, we have one more type of loads, aerodynamical loads. Weight, aerodynamical loads, maybe some load, depending on the type of aircraft, maybe some loads additionally if it's a supersonic aircraft with very high speed. Some loads may be results of aerodynamical friction and thermal changes. Plus, while evolutions of airplane in flight, we have inertial loads, no, and so on. All those loads regularly change during the flight, and in order to calculate, in order to start some calculations of aircraft structure, we may separate so-called flight cases into some groups, and actually in airworthiness documents, recommendations, it's given like this. We have them case 1, case A, case B, case C, and so on. Different cases of loading of aircraft, and for each of such loading we have charts of loads. And what next? Aircraft under these loads has like inner response. No, I trust you already have studied mechanics of materials, so you understand such a thing as stresses and deformations. So as a result of applying loads to the structural elements, whether it's airplane or automobile or fridge in your apartment, we have inner stresses and deformations in structure. What sort of stresses and deformation might be? This picture brightly illustrated the main types of loads and response of structures. It might be tension when we pull aside the structure, either we or not we, compression, torsion, and shear. Shear is on mechanical structure. It's easy to show. No, like two layers of structure, they are sliding with respect to each other, something like this. And actually, we're usually talking about what? We're talking about bending moment, and we're talking about torsion, and we're talking about shear forces. Bending moment. What is bending moment? No, not what is bending moment, but how it's may be understood. Look at this beam. Beam is bent right now, and on the outer loads, outer loads make beam to bend, and as a result, it's appeared a so-called bending moment, which try to make balance, try to move back this beam into original position. And look at layers of this beam. Outer layers, they are extended. You see, it's obvious that they are extended, they elongated, and they under the tension loads now. Yeah? And inner layers of this beam, they are, in contrary, compressed. They are compressed and they are shortened due to this outer bending. And as a result, they are trying to extend again. So bending moment, what I'm talking about, may be represented conditionally as the couple of forces, and this couple of forces acting one for tension and another for compression. So main kinds of loads right now we see. It's not comes directly to explanation, to our story about aircraft structures, but some things, this weird introduction, it was necessary to understand some things, why aircraft structure look like this. Very well. Let's come back to our slides to find the proper place where aircraft structure started. No, I have found, as I said, been searching for simple explanations for you. I have found some places with pictures, and mostly these pictures has appeared from books of Federal Aviation Administration. But that is the typical inner appearance of the wing. You might see now, no, it's a wooden wing. It's assembled somewhere in, I don't know, whether it's shop, whether it's garage. And similar picture explain us what it looks like. Very similar. Here is some pictures that show us not so brightly theoretical lines of different elements of the airplane inner structure. And in all those pictures, we might notice that it has longitudinal elements. All these elements, they have longitudinal elements, and they have transversal elements, which given shape to the airplane, either wing or frame. Is this inner structure always repeating the outer shape of the airplane like this or not? Actually, it's not. I should have started maybe even with another place here or here in order to say that here it's about fuselages, but similar story may be about any element of aircraft structure. Originally, if we looking back in the history of aircraft design, originally aircraft structures, they was not beam-like. Sound weird, but beam type structure, actually it's not a beam. It's empty inside. It contain some supportive elements, but it's called beam-like structure, beam structure. And another type of structure is truss structure. They are truss-like structure. But here you see truss-like structure, and here you see on this side, on the right side, you see beam structures, which actually more similar to the shell structures, I would say. Shell structures with some support. The very first structures of airplane, they was inside they were similar to this variant. And in this case, there are no elements which responsible for receiving, for loading with bending moments. All these sticks in different directions, they create complex spatial structure. They working only for tension and extension. For tension and compression. So they may be compressed, may be extended. That's it. Structure as a whole is able to work with torque and torsional loads, and practically no. We can't say that somewhere special elements for shear, for receiving the shear. And in contrary, the structure which has this beam-like composition, it's seems like it's works separately with different loads. What here is typical so-called spar or longeron, longitudinal element of the wing. It might be also in fuselage, but mostly they are in aerodynamical surfaces. Spar, another name for it, longeron. If you meet it in fuselage, it's called longeron. In English variant, in our language, there is no difference whether it's spar, whether it's longeron. We call it with the same name, longeron, which came from French maybe, and in a wing, in stabilizer, in fuselage, the same, longeron. In English, they usually distinguish. For aerodynamical surfaces, they call it spar. For fuselage and engine nacelles, they call it longeron. Well, the most general arrangement of the skeleton of aircraft. Let's come back to this. Where is the skeleton? Oh, here is skeleton. Now, this wheel or our body. Do imagine we have so-called spine, the main bone which responsible for bending of our body. It's counteract to bending. It may bend or in contrary, it may counteract to bending. And similar function and similar appearance has longeron. in the structure of the aircraft. These ribs, and that is difficult, or in contrary, more simple even in English, that they have similar names, the same name for different matters. We have ribs, we humans, and this whale, we have ribs, bones, which goes around our chest and no under skin, no? And which protect inner organs, which give shape to our body and protect inner organs. Something similar in the airplane, you see the same ribs, but they have different names depending on where they are. In the wing, they are called ribs. In the fuselage, they are called in English frames. And whole this structure, which consists of longerons, skins, frames, and stringers, all this structure of airplane is called airframe. Airframe consists usually, once again, airframe may be of, where it's disappear again. Airframe may be of truss-like type, truss type. What here is written the name, you see it. Truss type structure, and it may be beam-like structure. And those beam-like structure, they are also divided into some groups. As I already said you, inside of fuselage may be a longeron, may not be a longeron. Longeron in fuselage may exist, may not exist. But how the fuselage working with this bending moment, how it's counteract to bending? Depending on the loading intensity, let's say, depending on how big loads with respect to the area of the, like some elementary area of the structure, there are three different variants of beam-like frames, airframes for fuselages. One is called monocoque. Monocoque, like the whole egg. If we translate it from Latin, this weird word, take a look how it's written. Monocoque. What here is monocoque. And this shell-like structure, it's in this picture, it's even shown more more reinforced than that in real. Monocoque structure usually consists really of one shell, like shell of the egg or seashell, And the whole fuselage, which looks like such a shell, usually does not exist. Usually it's some portion of the fuselage where loads are not complex, not big, and where shape of the fuselage itself may be rather complex. And it's just really empty shell, rather thick, made of some stiff material, or it's made of composite material in modern conditions, for instance. And usually it comes about nose sections of the fuselages where we have some tricky shape, but we have no much loads. Monocoque structures, usually they have no neither longitudinal nor even transversal elements, but in this picture you see they have no only longitudinal elements, they have only transversal elements. Okay, that one also may be called monocoque. There is semi-monocoque, or it's translated like half monocoque, half shell-like structure, half eggshell structure. In this case, you will see, no, I am not agree with this picture, but whatsoever I use it. In this case, you will see both transversal and longitudinal elements, like it was, do forgive me, this jumping. What typical semi-monocoque right now in front of you. You not see any longitudinal. You see a lot of longitudinal elements which comes from us to the rear of this photo, but you not see any elements that differ from another. They are all equal, seems like, in their appearance. In contrary to the wing, look at this. In the wing, obviously, we might see some longitudinal elements more massive than another elements. Wait a second. Where is this? What? Bright picture. Visible also. There are some elements which are more massive than another longitudinal elements. This massive one, they are spar, or in fuselage they may be called longerons. They are for working with bending moments. And another thin one, which string from root to the tip, string from front fuselage to the aft fuselage. They are stringing, what like string in guitar, for instance. And these elements called stringers because they string through. They are thin. So what is called semi-monocoque, it consists of transversal elements, frames usually, and it consists of these stringers, but there are no longerons in the fuselage. All the stringers, they are practically of the same sizes, of the same cross-section. That is a structure which is called semi-monocoque. And wait a second. In case we have some of the stringers will be obviously more massive than another, and usually they are placed like 45 and in 4 places, but with 45 degree. Like, sorry, we'll go to drawing of my dreadful pictures again. Так, monocoque. Practically no any element at all, just some outer shell stiff enough to withstand the loads, and there are no any inner elements, just something like a shell. In case we have so-called longeron structure, in case of longeron structure, you will see thin stringers, rather thin, which goes through from beginning to the end. And approximately on 1/4, here, and here, like 2 o'clock, 5 o'clock, and so on, approximately in these places. It will be more massive structure. What they are really significantly differ in their appearance on other longitudinal elements, stringers. They look like beams in contrary to stringers. Those longerons, and they are responsible for bending moment receiving. Stringers are insufficient, really, or maybe absent at all in this case. And structure consists of skin supported with longerons and frames. That is the third variant. First one is monocoque, the shell, the only egg, just an egg shell. Third one has thin skin, massive inner longitudinal elements, frames, and maybe stringer. And semi-monocoque is consists of skin supported with dozens of these stringers and supported with transversal elements frames. It's for fuselage. Once again, remind you, it comes about three type of beam-like fuselage. And the most popular by now are these semi-monocoque structures. But what it depends on, what structure to use, what type of structure. Depends on so-called specific load. Z1 for rather little specific loads, Z1 for medium specific loads, and Z1 for high specific loads to the fuselage. In case you have beginning the front for a fuselage cowling, or somewhere at the end aft fuselage also cowling, something like cap at the end of airplane, it's feasible to use this monocoque structure. In case it's regular place inside of the fuselage, passenger cabin, cargo cabin, more convenient to use this one, semi-monocoque structure. And when it comes about the some special places with high loads, no, for instance, the place where you have the door, the cargo door, no, you know, this openable piece in the aft fuselage, ramp, so called, the cargo door in the at the end of the airplane. In this place, better to use this longeron type structure. So I'd like you to understand that all three types actually you may meet in the same airplane, just in different places of the fuselage. And typically all those elements, they are recognizable. I hope you will be able to recognize it with this. And transversal elements, typically they are called frames. Longitudinal elements may be either stringers or longerons in fuselage, and they are easy distinguishable by their sizes actually. Longerons more massive, more no, they are greater in sizes. Stringers, they are rather delicate elements actually. We will see it in photos next, and maybe not right now, but in our more practical classes. And in this case, you will understand, I hope, better. Quite clear that these beam-like structures, they should be used when you have skin, material of skin, which able to keep the shape. And why first originally structures like these truss-like structures has appeared? Just because people at beginning of aviation era, we have no people have no materials appropriate, convenient for creating, for constructing those structures with necessary shapes. And truss-like structures, no, especially one more important moment that it's too much maybe for beginners to understand, for those who just entering into aircraft engineering at all. But let's try at least to understand it in the most simple way. We are not we designers, designers of airplane. No, we are all aircraft engineers. We have so-called idea fixes, some idea fix, which the main ideas of all our activity, something like sort of crazy idea that permanently sitting in your mind. And designers has such crazy idea, the minimum of weight above the all. Whatsoever, in order aircraft fly, it should have minimum weight, minimum possible weight. And On this idea, on this principle, we are selecting and designing structures, we are selecting materials, and semi-please, no, so-called specific strengths. But look at this. No, maybe you already know such characteristic like ultimate stresses. Maybe you already, no, I think you already have studied mechanics of materials, so you know you're familiar with it's more simple to explain it to you than to real first years. With such diagrams, stresses, and deformations. And you know that behavior of material under tension, it's looks like this. And here we have some maximum possible stress material may stand with. And next, after this point, material just will be broken. And what light? I need to switch on light. I cannot see anything at all. Да. And what are characteristics of material for different materials? Now, for instance, structures made of steel, they have this sigma by point. There is a great variety with them, of course. Some middle one, approximately like 500 megapascals, MPa, and aluminum alloys, which has high strength aluminum alloy, which has strength around 300 megapascal. To provide aircraft strength, which one better to take? Seems like steel is better. But now let's see. Density, so-called specific strength. The strength of elementary volume of material, let's say. Density of steel is 7.8 ton to meter cubic. And density of this high strength aluminum is 2.7 ton to meter cubic. Once again, like it was with example of sound of speed and not real Mach number. We just need to see the ratio. It's some dimensional less characteristic we are going to talk about. We need to see the ratio. Let's use calculator. B. Y. Calculator. Oi. Too much. Maybe I need to ask it in our language. Not funny at all. Так. Oh, here is application. That should help us. No, do watch. 500, 7.8. What this value physically mean doesn't matter. Oi, minus. Why minus? I need divided. I'm surprised why it looks like this. Some unexpectable result I got. Yeah. 46. Some conditional strength of this material, 46 and 1. 46.1. And now let's try to do the same, but for aluminum alloy. 300 divide on 2.7. Why? What a bad surprise. Look, absolute value of strength of aluminium, of course, it's less, but uh, comparatively to its weight, aluminium seems like more strength to the same weight. It's so-called specific strength with respect to the weight of material itself. And if even we take here some more values, no, some more significant values, no, let's imagine that it was still with, no, let's see, still with 1000 megapascal breakpoint divided to 7.8. No, that is even better than aluminium already has appeared. No, really, you understand that normal range of strength of structural steel is around 500, 700 been used in structures. And it's appears that and aluminium also it's maybe much more strength and modern alloys on the base of aluminium which with the modern alloys which modern alloys on the base of aluminium, they have even less weight. What we talking about, that structure of, where is it, this structure, that truss-like structure, it's more weight effective for low speed aircraft. When aircraft fly with low speed, forces, aerodynamical forces, they are not big. You do remember this formula. If it's not disappeared, oh, it's disappeared. I will not search for it. Formula of Zhukovsky. The little, why I'm clicking permanently here? The little weight, you need little lift. If you need little lift, you fly with not high speed, for instance. Or no, that is not always true. No, first airplanes been flying with low speed, and they had rather low specific loads over surface of their structures. And in this case, more weight effective were these truss-like structures made of, practically made of sticks. And with appearing of structures, no, of another types of engines, with increasing the speeds, it appeared that these structures became too heavy. No, again, conditionally heavy. And people start studying another variants of structures and comes to these beam-like structures. And also I should say that this beam-like structures originally was made like skeleton, which was covered not even by very hard skin. It's maybe even fabric or some thick paper over the structure of skeleton, which consists of longitudinal and transversal elements. But with time, people have changed these rather soft materials to the much more harder one, to the metal materials. Okay, let's continue. Let's see some illustrations. Let's come back to the wing once again. What for? I repeated sometimes what is inner structure of frame of fuselage, of airframe of fuselage, but I have not repeated sometimes the same for the wing. Now, once again, inner structure of aircraft may be of truss type, like this, made of sticks, complex petal jointed, and maybe beam-like. Beam-like structure also may be of different types, but typically they have both longitudinal and transversal elements. These longitudinal and transversal elements, they are covered with skin, and altogether this grid of elements in longitudinal and transversal direction and covered with the skin, they work all together like one beam. And these structures in fuselage, they have names, nomenclature of these names, frames typically, and stringers for semi-monocoque structures, frames, longerons, and maybe stringers for longeron type of structure of the fuselage. And for monocoque structure, typically it consists just of the skin. No, in this picture, as we might see, it's said that it consists of so-called former or bulkheads. What is understood as bulkhead? It's usually it comes about the frame which just had no inner holes, like frame which at the end or at the beginning of the fuselage, for instance, or at the end of the fuselage, and separate some portion of fuselage completely from another portion. No, for instance, passenger cabin is finished with bulkhead. Passenger cabin, central fuselage, separated with bulkhead from the aft fuselage, where you have no pressurized cabin, for instance. That is bulkhead. Now let's come back to another illustrations. We need to see the names for the wing, and those names are not given here, да? Oh, they are not given here. They are given in other my slides. Take a look. Picture is bright, but as for me, not realistic. Longitudinal elements in this case, they are called spar, the most massive of them. Spar really looks like a beam, and they extend usually from the rod to the tip. Not like this in this picture. We will see another one next. So spar, it's not compulsory the only. It's usually comes about of couple of spar. If it comes about wing, or if structure is little enough, something like not even stabilizer, but something like flap, aileron, elevator, it's maybe the only spar there. In the wing of high loaded structures, like fighters, for instance, which supersonic fighters fly with very high velocities, do maneuvers and so on, and they are short winged additionally because it's more efficient in for drag. Now you do remember, I hope, that short wings on higher speeds, they have less drag than long winged aircraft. And in this case, it's maybe 7 and even dozen of spar inside. But instead of stringers, let's say, middle loaded aircraft, they usually have spar and stringers. The aircraft which fly with low speed, it's very similar to explanation about fuselages. Low speed aircraft, they usually have structure of wing which consists of spar and transversal elements, even without stringers. And in this case, skin is rather thin. And when you need to receive more loads, when you're flying with higher speeds, and as a result you have higher aerodynamical loads on your structure, then you need to reinforce the whole surface of the structure. And in this case, it's appeared first stringers. Next, these stringers became even more massive. It's so-called integral structure, monolithic structure of the wing, where you're already barely able to distinguish where are spar elements, where are stringer elements. So wings are also may differ inside depending on the speed what airplane fly with. But typically it consists of, again, longitudinal elements with name spar and stringers, and transversal elements, which has the same name as our body, ribs. Ribs and they given shape to the wing. Once again, take a look here. No, very well visible in this picture. Longitudinal element spar and transversal elements ribs. No, and some outer elements also mentioned here. Let's try to take a look into this picture. What do we see here? Was our newly obtained knowledge. I trust you already had some knowledge preliminary before even, because you not really first years, you studied already somewhere for a couple of years at least in your universities. You understand it comes about spar here along the wing, started from root and finished at the tip. It's so-called front spar. And here is rear spar. In this case, wing has two spar, front spar, rear spar, and ribs, which started from the nose of airfoil and to the trailing edge of airfoil. In real, of course, they consist of, I trust I made it, I have somewhere the photo. Oi, it's already too far. I thought I placed it here, the photo, maybe not. No, at least we might see this wooden structure people assemble. Look, here is extending the spar from beginning to the from the beginning of photo to the along the span, to the back of the photo, and rear spar. And those structures which are ribs, they actually divided onto subpieces. Spar never cut. Spar is important element working with bending moment, and it's the whole beam. Rib consists really how they intersect here in this picture. Just skim with intersection. But really, a rib consists of some pieces, of some sections. Nose section, middle section, and rear section. In case it will be more spar, a rib will be divided into more sections. And stringers, no, in this structure they are not shown, but in case they goes under the skin, and in case they exist under the skin, stringers will also not to be cut. They passing through the ribs if necessary. Rib has cutouts. They have some something like holes additionally in order to pass stringers. So longitudinal elements are more important than transversal elements. They are working with bending moments. They are important to resist to these loads of tension and tension and compression loads, the whole structure. And torsion is taken with structure as a whole, not with some particular element. Structure as a whole, all this box-like structure is able to resist torsion. When it comes about shear usually is received with thin elements which exist, which represented by ribs and by spar. Let's see one more explanation here, what spar looks like. And what spar looks like. Look, why they have such weird shape. Why it's not just, I don't know, some rectangular or even squared in cross section. Once again comes into drawing. Let comes into drawing. I hope I'll be successful in this drawing right now and may explain it properly. No, I trust you already know mechanics of material, so you may understand it. Here is a rectangular beam, and as I'm already said you, what bending moment looks like. No, look at this. Couple of forces. Here it's extension, here it's compression. And quite clear that some what in cross section. Look at this. In cross section, oi, better just an axis. In cross section, those forces plus minus, no? Tension, compression. Somewhere outer layers they are most extended, these outer layers. Somewhere we have zero line where there is no extension or tension, but zero bending line. And somewhere we have the maximum compression forces. And distribution of the husband is calling. He's outside home right now. I will finish in some minutes and answer him. Distribution of these forces is unequal in cross-section. At the outer layers we have maximum forces. In the inner layer we have practically zero forces. You know this. And do imagine that you took material, no, you took piece of material which has rectangular shape. The outer layers of this material, they resist to loads intensively, they are working, and inner sections of material, somewhere here, lazy layers, they are idle, they do nothing, but they have weight. And I hope you do remember what did I said already about designers. Designers are all designers of airplane, always crazy about minimizing the weight. Structure, each element of structure should work effectively, receiving the loads, counteracting the external loads. But you shouldn't have any structural element on board which doesn't work because it has weight. Weight of this element resulted in additional fuel for transporting of this element, which doesn't work. And we have a lot of considerations, we have a lot of rules, details, tricks, how to save weight in structure of airplane design. And one and basic maybe that you already get used to, maybe you will get used to, is specific cross sections of structural element. For instance, this element SPA, this longitudinal element which working with bending moment, better to take with a shape unequal with respect to what we have already, I hope, understood. Here, more efficient will be cross-section. No, I mean efficient in understanding weight loads ratio, loads to weight. Yeah? Such a structure will have less weight, this cross-section, than rectangular structure able to counteract to the same loads. And if you take a look to if you take a look on the appearance of wing spa, you see practically the same thing that I said already. It's so-called double T shape. It's maybe channel shape also, something like this. depending on variance of placing of the spar, depending of load's intensity and so on. But typically they are not solid rectangular or solid square elements. Same consideration will be for stringers. They have another appearance. Usually they not looks like double T, but they may be either T-shaped or corner-shaped, L-shaped, or they may be V-shaped, even something like this under the skin. But certainly they don't look like pieces of solid material, rectangular or squared. Certainly not, because it's not weight effective. And what we need to see here more. Let's take a look in cross section. What these two cross sections. There are two rather similar pictures. But what is the difference between them? I hope you do remember what did I say about fuselage. There are monocoque structure, semi-monocoque structure, and longeron structure. Same thing may be said about the wing, but wing, in contrary to fuselage, it has another name for these types of structure. No, practically it has another names. Look, what is longeron structure or spar structure, no, spar-like, spar-type structure of the wing? What it's represented on the top picture. You see only ribs, which responsible for holding shape, for keeping shape, and spar, main spar, rear spar. One is double T, another is C channel, and channel profile. And what do we see in the bottom picture? We have some spars, even some spars we have, but they are not so massive. They are much more delicate. And by their size, they already practically barely distinguishing from stringers. Stringers has appeared, you see. Stringer has appeared, and stringers take part in the counteracting to the outer loads together with the skin and supporting skin. And that is so-called torsion box structure. No, you may meet it with different names in English literature. No, idea is here bending moment received and counteracted, let's say, only with spars practically. And in this structure, no, it's called box beam structure here. It's so-called torsion box, and this torsion box structure consists of spars and stringers. No, of course, they are all interacted with ribs. Not visible here. Where it's visible. Where it's visible. It was visible before. No, not like in these structures. So they are working all together, like the whole structure, and each element in structure of, here is it's visible at last. I have found it. Each element of longitudinal and transversal structure, they either in fuselage or in wing, stabilizer, flap, whatever, they are compulsory joined to each other. They are not separate elements. They are all joined with additional elements. The names of those additional elements of these real parts: stiffeners, struts. Again, this word struts you already heard. In case when we talked about the whole wing, they may be called. Let me to find where is this. They may be called struts. They may be called stiffeners, and the shortest of them usually are called knees. And you see it's again some referring to our body, as you might understand. Knee is something that we have in our body either. Very well. And let's come back to this beautiful picture that I said I have found. In the book that not even the whole book I recommend you to read, but this structure, this chapter, aircraft structures, to read or at least try to read it to understand more about what I trying to explain you. No, at least you need to understand nomenclature, and at least you should be able to recognize those structural elements in real structures at the end of our study. Like elementary, recognize them. What I've been explaining you about the types of structure, like truss-like structure, beam-like structure, you see here those beautiful pictures, quite the same. And additional elements mentioned here, it's like doubling pieces of skin that doubling reinforces the places of joining of transversal and longitudinal elements, which are already joined with stiffener, knits, and so on. Now, whatsoever there are additional elements in the not everywhere, but in some places they are given. You see, given with the name gussets, pads, and so on. Now, typical structure of wing looks like this. We have longitudinal elements. Right now it's visible. It should be extended along the wing. And transversal elements, longitudinal elements, wing, stabilizer, flap, elevator, whatsoever, any aerodynamical surface, usually called spar. Transversal elements, usually called ribs. There are another names, and these another names depending on the thickness, depending on the place where it's used. It may be called diaphragm, for instance, when this rib is rather thin and delicate. No, about spa, I'm already said you. I meant to show you what it consists of, and even explain it why it consists like this. But I forgot to mention names. Look, spa in real it consists of pieces as a rule, and these pieces names they are called cap, upper cap, bottom cap, and web. No, like whatsoever, but in English it's called like this. This thin shell which join upper cap and bottom cap, it's called web. Struts or stiffeners, what right now you see them here. And actually these stiffeners, I hope you understand, they are necessary to join ribs here, for instance. One of their function additionally, that you might join ribs with the help of those stiffeners. But additional function to join stiffeners, to join ribs actually to the web. Real function of these stiffeners would exactly to make web stiffer, to add stiffness. Once again, the same strength, like what I tried to explain you here. The same strength may be in cross section, rectangular cross section, and like tension strengths will be the same area. What let it be done? We take the same area, but this area distributed in different shapes will give different results with when you're working with bending moment. Um, Let's try to find the empty place, or let's clean everything what I made here right now. It's already two elements of aircraft strengths, actually. Aircraft strengths tightly intertwined with aircraft design, and practical not possible to discuss one without another. Look, if you have area of material like this, and you distribute its, no, like you extend it here, thin web, and some piece will be as a cap here and there. The whole area will be the same, but this one may withstand more high loads, especially when it comes about bending moment. That one would, with the same area, seems like it's impossible. Да? For tension, they will be quite the same. For tension, sigma breakpoint will be the same in this cross section, in this cross section. But when it comes about both tension and compression, means bending moment, that one will be more effective than simple like this. It will be less weighted. It may withstand higher loads, and in order to have more stiffness of such structure, we may comes into some tricks like, what if we extend it here, instead of making thick web, in my picture it's rather thick, this web, let's remove some area of this web. Let's take material, some portion of material we replacing, like we thinning the web, but the same material we will place here in the view of additional transversal elements, these struts, like little ribs in the spar structure, as you might see it here. And in this case, it became even more stiff. No, usually we show for our beginners those things immediately in the piece of paper. Do imagine that you took piece of paper, place it vertically to the table, and move hand to this piece of paper. What happened to this piece of paper? It's bended under your hand. Actually, it's bended even without your hand. No, you understand. As if you apply load to the piece of paper, to its inside, to its butt, and it has big area, but it's just plain simple piece of paper, or something like this. Or, I'm wrong. Better to draw it like this. And you apply a force from top. Of course, it's just bucklet, and that's it. Take the same piece of paper and fold it. Do something like L shape, and try to apply the same load. What it will be? It's already bucklet less. Do fold it once again. Just make some simple experiment at home. Fold it sometimes and apply the same load. And you will see that this time maybe it's already able to withstand load. It doesn't buckling. This changing of cross section with the same area of cross-section, but changing the shape of cross-section. It's a very interesting effect, and in aircraft strengths, for aircraft strengths, in aircraft strengths as a science, let's say, they study those cross-sections to understand. Oh, I'm afraid. These phone calls, it's disaster, really. To forgive me. They may have disastrous results. In aircraft strengths, properties of different cross-sections are studied, and we selecting the most effective one. What does it mean, most effective? They are effective in idea that the same weight of material will be able to withstand higher loads. Once again, let's come back and we'll finish at last this portion of our class. You see here historically developed shapes of spars, and as I'm already said you, with the same area of cross section, this one or box like or this one is more effective than simple rectangular one. And here you see typical cross sections of metal spar which exist by now. Usually they are not made of one piece of metal. In real life they are usually made of different sub elements of different parts, and these sub elements in turn they are usually made of so-called standardized work pieces. And in design of, no, it's maybe too early to discuss with you. In design, while designing of airplane, designer already think forward about how this spar next might be manufactured. And of course, designer may draw everything. Designer may mention any shapes, any structures may draw, but in case it's non-realistic, in case it's difficult to produce, no one will produce this airplane, or this airplane in manufacturing will be too much expensive, and if even someone risked to produce it, no one next buy such airplane. So designer think forward while process of designing about future manufacturing of structures, and usually those structures they have rather their sub elements, their parts. They have rather simple shapes. No, besides of those elements which responsible for aerodynamical airfoils. Wherever it's possible, designers simplify shapes of parts of aircraft in order these parts next may be produced from standardized workpieces like sheets, extruded profiles, and so on. No, wherever it's possible. But the very first basic idea of any designer, of course, is to provide the minimum of weight. No, and once again, let's see what is the general, what now we see the wing from top. And you see here some names. No, nomenclature of the wing, so-called. Look, longitudinal element, spar. Here is the front spar, the rear spar. How I understand where the front, where the rear, not only by because I might read something. Now, what I hope it's visible good for you. But on the trailing edge, there are some hinged elements shown. Maybe aileron. Yes, aileron. You see that the piece of wing is like cut out, and you see here element on the hinge. So that is trailing edge, that is leading edge. Front spar, rear spar, some ribs. Ribs may be also different in the massiveness, in the how much bulk they are. in their sizes. In case something joined in the place, near the place, at the place where this rib is, this rib will be more massive. It's something like just frame in fuselage and bulkhead. But take a look. Maybe the same structure approximately in this area near the tip. We see spar and the end of the spar, rear spar, and we see ribs here. Of course, real structure is much more complex than any schemes, any simplifications. But at least we need to get used to watch this and to understand it. But look at this. What do we see? Longitudinal elements of the wing, spar, and another spar. And transversal elements, ribs. We see them by lines of rivets here, and here skin is partially uncovered, and we see the shapes of ribs. Look at this. What do we see here? A spar. Here is T-shaped spar. Here, maybe even not T-shape, but more complex. You see, it's like T at the top and L shape at the bottom. Any configurations are possible, depending on the loads, depending on the sizes of aircraft. You see front spar, you see rear spar. They extend along the wing. And what do we see in more details? We see what? Ribs. But do take a look, ribs like they are penetrated with another elements. I need you to understand it's not clearly shown here. There, no, without scheme, it's not real structure. Without cutouts for stringers. Stringer comes through beginning to the end without any interruption. If only there will be some what the analog like bulkhead in the fuselage, there are maybe some wings elements, like rib at the beginning of fuel tank and at the end of fuel tank. In modern passenger and cargo airplanes, usually fuel is placed inside the wing. It's the same consideration that no any element of airplane should be idle. Wing of cargo or passenger airplane, it has big size, it's high enough. This thickness of the wing, it's very big for passenger airplanes, for cargo airplanes. In case it's empty and you are just transporting the air inside the wing, and somewhere else you need additional place for fuel compartment, it's completely inappropriate. That is why inner space in the wing usually taken by fuel. Of course, it's special design, it's pressurized, it's everything is sealed and so on. But somewhere there is beginning of this fuel tank and end of fuel tank. In this place, stringer may be interrupted by rib. In all other places, stringers are continuous from beginning to the end. They are important longitudinal elements. Once again, spar, rib, stringer, and skin. Here we see the wing as a whole, and take a look on the, let's imagine, where the spar extend from the root to the end, from the root to the end. Along the airfoil we have ribs, and maybe we have also the stringers here. No, that is already explanation of another type of structure. Look, I said as a rule, sometimes, usually, typically, as a rule, but really variety of this structural design is undescribable. And in this case, what here is they demonstrate in the picture so-called honeycomb structure. honeycomb structure and sandwich structure. When thin, very thin skin is supported with also very thin, made either of foil or even of paper. No, usually it comes about synthetic paper, no, doesn't matter. With very thin walls elements, which has specific shape. Why it's honeycomb? Because it really looks like honeycomb in cross section. And this extremely thin, extremely light structure, it will have very high strength. I have not seen here is honeycomb structure in this book somewhere, not far. So let's try to take a look immediately. Immediately here, sandwich structure, honeycomb, sandwich structure composite. In pictures, I trust it's more understandable than in my explanation. You see, this honeycomb structure altogether very thin, like foil at all, layer of skin at the top, at the bottom, and these honeycombs made of very thin materials, very delicate materials, like as I said you, it's maybe metal foil, it's maybe composite material, it's maybe even special polymeric paper. And altogether, each of these, no, altogether they have great strength. Each this element is extremely delicate and you may break it by fingers. But altogether they are able to create strong structures and withstand the aerodynamical and weight loads. Of course, they better work with so-called distributed loads, no, for instance, aerodynamical loads, but able also to withstand the torsion loads at least. And here is example once again of structure of fuselage and of airfoil-like structures of the airplane, wing, fin, stabilizer, all the high-lift devices like flaps, for instance, or slats, all the control surfaces. Usually, typically, they have longitudinal elements and transversal elements which containing, no, keeping the shape. Longitudinal elements, once again, bending moment, transversal elements, shape and shear, altogether structure work for the torsion, and all this is covered with the skin. Skin may take part in receiving the loads, may not, because skin may be made of metal, and in this case, and even skin made of metal may have different thickness, able to withstand the loads or disabled to withstand the loads. Or skin may be made of any another material, including even fabric and paper, like in early structures of airplanes. And in this case, quite clear, it's not working with loads, it's only create some sort of envelope over the airplane. Actually, these truss-like structures, they've been like inner truss, which surrounded with some envelope, let's say, or even without it. You might think that fuselage consists just from these pipes and not even covered with any additional elements like skins. Once again, I repeat the nomenclature of elements, and let's stop on this. Fuselage consists of frames and stringers, semi-monocoque fuselage. In case it's heavy loaded place of the fuselage, it's maybe of another type of scheme, and it's so-called longeron type of fuselage. In this case, it has frames, 4 longerons, or two longerons, depending on how much you need. For instance, you have cut somewhere. No, because they are placed. I hope you do remember what did I show. Maybe it's too difficult now to find where I dropped this picture. Oh, here is, because they are placed in these places like one quarter, approximately 45 degrees of each quadrant, and of circle. And in case you don't need to reinforce the top surface, for instance, if you have some cut in the bottom, in this case you have two spa here, or two longerons, do forgive me. It comes about when it comes about fuselage, they are called longeron in English. When it comes about aerodynamical surfaces, the same function of element, but they typically called spa. Spa and ribs here, longeron and frame here. Stringers, they have the same name here and there. No, and bulkhead, once again, it's the same frame, but this frame has no inner cuts. It completely separate one area from another area. It's like more massive frame. This most massive frame, they are usually called bulkheads. And it was somewhere the structure for empennage, if I'm not mistaken. Maybe I'm mistaken. No, right now, maybe we will finish on this. Once again, show you those pictures. Once again, remind you this weird name, same